Welcome to the third video for our first class session. I believe we left off looking at the 1s orbital. In fact, we did a plot of r squared times the square of some radial component of the wave function that describes the position of the electron in the 1s orbital, which would correspond to something like a probability of finding that electron. So we're going to do the same exercise for the 2s orbital. We'll do r squared of the radial function squared for n equals 2 and L equals 0. And remember, when we took a lengthy discussion of the form of the wave functions, we decided that at some point the wave function for our 2s orbital dropped to 0 at some distance r from the radius. And in fact, that's what we see when we plot this r squared times the radial function squared. We see a node that occurs at this particular distance from the nucleus, where psi goes to 0 in terms of r over a naught, and the wave function changes sign. And that node is represented as the boundary between the inner shaded sphere and the outer clear one on this depiction of a 2s orbital on some sort of Cartesian coordinate sphere. It almost looks like a jelly donut in terms of at least the signs for the wave function that you would encounter. So what is also interesting to point out about the 2s wave function is you see a high probability at approximately 5.236 units of r over a naught, which is significantly further away than we saw for the highest probability of finding the electron in the 1s orbital. What this means is the 2s orbital electrons are more likely to be found further from the nucleus, and that is characteristic for electrons that are higher energy. Now we could go over the same sorts of exercises for the p orbitals, but I thought I would just give you a plot for what they look like on Cartesian coordinate systems. So we have three different axes. So there are three different p orbitals. There's the 2pz, 2py, and 2px, and they are represented as typically lobes, a positive lobe and a negative lobe. For the 2pz orbital in particular, we have a positive lobe that rises above the xy plane, and then we have a negative lobe that goes below the xy plane along the z-axis. The xy plane, in fact, could be described as a nodal plane. That is, you cannot find electron density in that xy plane. It drops to 0 for our 2pz atomic orbital. The 2py orbital looks very similar to the 2pz orbital, except it lies along the y-axis, and the xz plane is the nodal plane. The 2px orbital similarly looks like the 2pz and the 2py orbitals, but it lies along the x-axis, and the yz plane is the nodal plane. Now, of course, when we draw our p orbitals, we sort of approximate these lobes, and a p orbital is a much more complex thing than just some lobe extending a certain distance from the 0, 0, 0 coordinate, or the nucleus. This is actually a diffuse cloud that extends infinitely far away along the x-axis and infinitely to the right and to the left, positive y and negative y values. But the further and further away you get, the more and more diffuse you get, or the lower your probabilities for finding an electron. So we typically truncate our p orbitals and resolve them as sort of defined lobes. But it's nice to appreciate the deeper reality for them. So I think we'll go ahead and continue on, and hopefully we will cover the off-bow principle and Hund's rule before the end of this video session. I know it's difficult to stay focused. So the closer to the nucleus an electron is, the lower in energy it is. If you remember from general chemistry, our 1s orbital is lower in energy than our 2s orbital. So typically the electrons are closer to the nucleus, as we sort of observed with our interesting plots. The 2p orbitals are higher in energy still than the 2s orbitals. I've drawn them all in line with each other at the same energy. We say that they are degenerate if you have atomic orbitals or molecular orbitals that possess the same energy. Then we move up to the 3s orbital and then the 3p orbitals. The number of electrons you might find in a shell is given by the formula 2n squared, where n is the shell number, that is the energy level. And so here we have the off-bow principle, and that principle says basically lower energy shells are filled first. After the off-bow principle, it's kind of interesting to encounter the Pauli exclusion principle. That is, no two electrons can have all four quantum numbers be the same. And I think you may remember from general chemistry diagramming out electron configurations for various elements. Hydrogen has one electron and a 1s orbital. Helium has the 1s orbital filled, so 2 electrons. So 2 times 1 squared is 2. That's the number of electrons that you can fit in your 1s orbital. When we go to lithium, we have 3 protons, so we must have 3 total electrons for a neutral lithium atom. So we put 2 in the 1s orbital and then 1 in the 2s orbital. You can try beryllium and boron on your own, and you could also consider abbreviating electron configurations in terms of noble cores. So for lithium, we all know helium is a noble gas. We can symbolize that 2 electrons in the 1s orbital as a noble core of helium, followed by 1 electron in a 2s orbital. And for our last video, we will probably encounter Hund's rule and the Lewis bonding model, and then move forward to class 2.